In this problem, we're simplifying four separate expressions. Let's go over them one at a time. Starting with the first. In this problem, what occurred to me when I rationalized the denominator is that 1 over radical 2 is the same as radical 2 over 2. And once I rewrote the problem this way, I thought about what the inverse cosine means. And we're looking for an arc length or a number between 0 and pi whose cosine is radical 2 over 2. This value should seem familiar to you from our favorite 16 points on the unit circle. And out of all 16 points on the unit circle, specifically those between 0 and pi, I should say, the only terminal point whose cosine is radical 2 over 2 is pi over 4. And that basically just comes from memory and the use of the unit circle over and over. Let's take a look at our second problem. The inverse sine, by definition, is the number between negative pi over 2 and pi over 2 whose sine is that argument, in this case, negative 1/2. Negative 1/2 should also look familiar to you from our 16 favorite points on the unit circle. And there are actually 2 points on the unit circle that have a sine or a y-coordinate of negative 1/2. But since we're looking for one between negative pi over 2 and pi over 2, this is the only one that qualifies. Now, it's typical for students to think of 11 pi over 6 as this point. And while it is true that the arc 11 pi over 6 terminates at that point, 11 pi over 6 is not a number between negative pi over 2 and pi over 2. So we have to find an arc or a number that terminates at that same point between those values. In other words, we're going to have to express it, in this case, as a negative arc or a clockwise arc. Thinking of it that way, one quickly realizes that the arc negative pi over 6 also terminates at that point. And because negative pi over 6 is between negative pi over 2 and pi over 2, then that qualifies as the answer to this problem. Let's take a look at the third problem. The first thing that caught my eye was the squared above the tangent. And just to remind you, the tangent squared of any quantity is literally the squaring of the tangent of that quantity. And it's worth thinking about the squared that way because it reminds us that in order to do this problem, we're going to have to compute the tangent of the inverse cosine of 1/4 first. And then whatever answer we get for that, you may see that thing in red, whatever answer we get for that quantity in the parentheses in red, then at the end we'll square that number and be finished with the problem. So let's put the main thread aside here and just focus on the problem without the squared. In order to compute this, I'm looking at the right side of the screen here. I'm going to have to work from the inside out. I'm going to have to try to find the inverse cosine of 1/4. That literally means this by definition. Now, it may occur to you, as it did to me, that out of our 16 favorite points on the unit circle, none of them has an x-coordinate or a cosine of 1/4. So we're looking at other points on the unit circle here. So I decided to try to draw a picture of the inverse cosine of 1/4. Here's my unit circle. Here's 1/4 on the x-axis, approximately. And since I'm looking for an arc between 0 and pi that terminates there, my arc must terminate at this red point, and therefore this arc shown here is the inverse cosine of 1/4. Just for brevity, let's just call that arc length A. Now, because this point is not one of our favorite points on the unit circle, we don't know what A is in terms of as a simplified expression using pi, say, for example. In fact, without a calculator, there's no good way to find the inverse cosine of 1/4 or to find the length of this arc A. But I don't really need to, because this problem isn't asking me for the inverse cosine of 1/4 as much as it's asking me for the tangent of that value. But remember, I'm looking for the tangent of this arc length, ultimately so I can square it and be done with the problem. But first, before we square it, let's just try to find the tangent of this arc length. Now, you might think we need to know the arc length to do that. Not really, because the tangent of any arc length is the sine divided by the cosine. So if I can find the sine and the cosine of that arc, then I'll be able to find the tangent. Well, I already know that the cosine, or the x-coordinate, is 1/4. So now I have to find the sine of that arc. Well, to find the sine of that arc, or the sine of A, I can use my main Pythagorean identity, plugging in 1/4 for the cosine, and doing all of the usual algebra here. I won't explain each step. Hit pause if you want to examine it more closely, and I'll proceed. It's worth noting that the sine is a positive number because A terminates in quadrant 1. But now that I know that the sine is radical 15/4, I can plug that in to the equation on the right. And I'll do some basic arithmetic, which I didn't show here, to get the tangent of A is radical 15. But remember, A is that arc, the inverse cosine of 1/4. So now I've just computed the tangent of that arc. In other words, the quantity on the left side of the screen in the parentheses, you may see it in red, I've computed that just now to find out that that quantity is radical 15. And as I promised in the beginning, having found that quantity, now I can square it. That, of course, works out to just 15, which is the final answer to this problem. Now let's take a look at our last of 4 parts to this problem. Working from the inside out, the first thing that occurred to me is I should try to find the inverse cosine of 5/13, which means this. Once again, it has occurred to me that this arc does not terminate at one of our favorite 16 points on the unit circle. And because it doesn't terminate at one of them, I can't find this as a simplified expression using pi, like you normally would if it did terminate at one of your 16 points on the unit circle. But even though I can't find the inverse cosine of 5/13 numerically, at least not without a calculator, I can draw a picture of it and get a sense of this problem. So if I'm looking for an arc whose cosine is 5/13, it must terminate at a point whose x-coordinate is 5/13. So look at the x-axis. I placed 5/13 about there to show that it's a little less than half, which it is. And because I'm looking for an arc between 0 and pi, my arc must terminate at this point, and therefore my arc must be this length. I decided for simplicity to call that arc length A. Again, I don't know what A is as a decimal or a simplified number without a calculator. Now, this problem runs into a little bit of a snag because of this 2 here. Because that 2 is there, I can't apply the sine function yet. Well, wait a minute, doesn't that mean I would have to find the quantity in green, or that arc length, and then double it? And how can I double something if I can't find it? Well, that's good logic, but watch how I decided to get around that. Again, calling A the inverse cosine of 5/13, just to have less to write for simplicity, I can now proceed by using the fact that the sine of 2 times any arc always equals this quantity. That's just an identity that we use quite frequently in this class. And so if I can compute the quantity on the bottom, then I will have computed the sine of 2 times a, which is the quantity I'm trying to compute in this problem. So clever how I'm using an identity here to avoid having to multiply a by 2 when I don't know the value of a. The nice thing about the expression on the bottom is I can replace the cosine of a with 5/13. And now if I can find the sine of a, I can finish this problem. Well, as usual, using our Pythagorean identity and plugging in the cosine of a, and doing all of the usual algebra, which you can pause and examine for yourself if you'd like. Let's proceed. That tells me what the sine of a is. And now that I know the sine of a, I can continue calculating this expression and doing a little arithmetic and simplifying. I now have that 2 times sine a times cosine a is 120 over 169. But that was precisely what I was trying to compute in the first place, and therefore that is the answer to this fourth and final question. And that completes this problem.